There is no general roadmap for designing a gas turbine engine. The design stage can depend on various conditions. For instance, the experience of the manufacturing company and the design team's individual, as well as the nature of the project itself, are significant influencing factors. A project for a revolutionary new engine requires more analysis and iteration compared to modifying and upgrading an existing engine. Nevertheless, there are general representations of the design process that can be informative and useful, one of which you can see in the figure. In the training courses related to gas turbine engines, we aim to address all the topics presented in this figure in detail. Therefore, I recommend those interested in this exciting subject join the channel to stay informed about the topic discussed in the videos. There are two main ways to obtain the general specifications for an engine that needs to be built: customer requirements and market research. Customer requirements are one of the primary and perhaps most important reasons for creating a gas turbine engine, typically stemming from orders placed by large aircraft manufacturing companies. In designing gas turbine engine, customer requirements play a critical role in shaping the development process. These requirements include various design criteria that often encompass operational needs and regulatory compliance that must be met to ensure the effectiveness and reliability of the engine. Customer requirements significantly shape gas turbine engines design by dictating performance criteria, specific functional characteristics, optimization strategies, stockholder interaction, and technological innovations. By focusing on this requirement throughout the design process, engineers can develop engines that not only meet customer expectations in a competitive market but exceed them. Customers provide criteria based on the missions and needs of the aircraft, such as flight speed, altitude, and aircraft weight, in a request for proposal list. Engine designers then use this list to conduct preliminary studies. Effective market research in gas turbine engine design is essential for aligning product development with industry demands. By understanding market dynamics, customer needs, competitive landscapes, regulatory frameworks, and employing robust research methodologies, manufacturers can innovate effectively and maintain a competitive advantage in an evolving aviation landscape. However, the importance of this method is less than that of customer requirements. Preliminary studies show cycle and type of turbo machinery layout. The working cycle of gas turbine engines is Brayton cycle. At this stage, type of engine is selected, which can be one of its four main types. Preliminary studies in gas turbine engine design are crucial for making informed decisions about thermodynamic cycles and turbo machinery design that may be either axial or centrifugal. By carefully analyzing these aspects, engineers can optimize performance, enhance efficiency, and ensure that the final design meets customer specifications and legal requirements. This foundational work lays the groundwork for more detailed analysis and refinements in later design stages. Thermodynamic design point studies. The engine design begins with parametric cycle analysis, where all design choices are carefully examined. At this stage, dimensions and sizes of the engine have not yet been determined, making it known as a rubber engine, which can take any size. This involves using parametric cycle analysis to estimate design parameters such as specific thrust, while considering design constraints like maximum allowable turbine temperatures and achievable efficiency across various operating conditions such as ambient pressure, temperature, Mach number, as well as design choices like compressor pressure ratio, fan pressure ratio, and bypass ratio. This analysis focuses on defining a set of conditions referred to as design points. Design points are expected scenarios where a gas turbine engine will operate during most flight scenarios, such as takeoff or maximum output power flights. The outputs from this stage are critical parameters that define the performance and characteristics of a gas turbine engine. These parameters include mass flow rate, the amount of air passing through the engine per unit time, total pressure and temperature, measured at various points within the engine, providing fundamental knowledge about thermodynamic conditions. Compressor pressure ratio, the ratio of pressure before and after the compressor, significantly impact overall engine efficiency. Turbine inlet temperatures must be decided based on methodological constraints. Specific fuel consumptions, a measure of fuel efficiency defined as fuel required to produce a certain amount of thrust. Thermal efficiency, indicate how well an engine converts fuel into thrust. Power output represents the total mechanical power produced by the engine. Engine thrust, propulsion force. Off-design performance. This stage refers to operational conditions of a gas turbine engine that deviate from predetermined design points, typically defined under specific environmental conditions and performance parameters. Understanding off-design performance is crucial for ensuring reliability and efficiency of gas turbine engines under various operational scenarios. The aerodynamic design of gas turbine engines after the thermodynamic design point studies is the most important stage that involves several engineering disciplines, including aerodynamics, thermodynamics, heat transfer, and material science. The design of individual components, such as compressor and turbines, follow the systematic approach. For example, in compressor design, the aerodynamic loading and the number of compressor stages are determined first. The turbine design must also ensure that, in addition to extracting the necessary energy from the hot gases exiting the combustion chamber to drive the compressor, these gases can also generate thrust. An effective aerodynamic design minimizes the drag losses and ensures a smooth airflow through all sections of the engine. The shape and angle of the blades in compressor and turbines are optimized using computational fluid dynamics to enhance performance under various operating conditions. In general, it can be said that the aerodynamic designs of gas turbine engines is a multifaceted process that requires careful consideration of various engineering principles. By integrating aerodynamics with thermodynamics and structural analysis, designers can create efficient engines that meet optimal performance requirements for different applications. Continuous advancements in computational techniques increase the accuracy and efficiency of this complex design process. Mechanical design. Mechanical design in gas turbine engines involve a complex interplay of material science, structural engineering, and thermodynamics. Engineers focus on component integrity, stress management, thermal performance, and integration to ensure turbines operate effectively and reliably through their intended life cycle. This meticulous approach not only enhances performance but also significantly contributes to safety and longevity in gas turbine engines. Control system studies. Control system studies in gas turbine engine design are vital for ensuring efficient operation, safety, and reliability. By employing advanced modeling techniques, complex control strategies, and robust safety mechanisms, engineers can develop systems that effectively manage the complexity of gas turbine operations across various applications. This study not only improves engine performance, but also significantly enhances operational stability in power generation and aerospace applications. Detailed design and manufacturing. The detailed design phase in gas turbine engine development is a comprehensive process involving material selection, precise engineering specifications, advanced manufacturing techniques, and rigorous testing protocols. By focusing on these elements, engineers ensure that gas turbine engine not only meet performance expectations but also adhere to the highest standard of safety and reliability throughout their operational lifespan. This phase is critical for transition from conceptual designs to fully functional engines capable of operating in harsh environments. Design modifications. If tests conducted on various components do not yield satisfactory results or do not meet designer expectations, engineer must implement modification on the engine. Design modification in gas turbine engine are a vital aspect of the development process, ensuring that the engine remain competitive in performance while complying with environmental standards. Through systematic enhancements to component control system and operational strategies, engineers can significantly improve capability while addressing emerging challenges in aircraft applications. Restressing mods. Reevaluating stresses and modifying them focuses on optimizing stress states within engine component to enhance durability and performance. By employing advanced analytical techniques, alongside appropriate material selections, and informed design modifications, engineers can improve reliability and efficiency of gas turbine engines. Test platforms. Test platforms are essential tools in the gas turbine engine design process, allowing for comprehensive evaluation and validation of critical components. By simulating real-world operating conditions while providing accurate performance data, these facilities help engineers to investigate and optimize in design for efficiency, reliability, and compliance with regulatory standards. Aerodynamics mods. If aerodynamics issues arise after reviewing results from various equipment, especially turbo machines, then a component with aerodynamic concern undergoes further scrutiny or even redesign. Through thorough analysis and reshaping blades designs along with inlet configurations and flow management strategies, engineers can significantly enhance efficiency while reducing losses and improving thrust capability. Integrating advanced simulation tools like CFD, along with precise testing methods, ensure these changes are effective and reliable before full-scale production. Updated and modified versions. Updated versions of gas turbine engine are crucial for meeting increasing demands for efficiency, reliability, and environmental compliance within propulsion manufacturing sectors. Through targeted modification that enhance component performance while extending maintenance intervals and reducing greenhouse gas emissions, manufacturers can significantly improve operational capabilities of existing gas turbine platforms. This upgrade is not only benefit operators by reducing costs, but also contribute to environmental sustainability goals. Production. The production phase of gas turbine engine is a multifaceted process involving meticulous planning, precise manufacturing practices, thorough testing procedures, and quality controls measures ensuring each engine meets high-performance standards. By focusing on material selection, component fabrication techniques, assembly methods, along with comprehensive testing protocols, manufacturers can deliver reliable, efficient gas turbines for diverse applications in aviation. Fuel services. Fuel services represent a critical aspect of the gas turbine engine design process, focusing on maintaining reliability efficiency through comprehensive support activities. By providing maintenance services, emergency response, technical expertise aligned with performance optimization services field, service teams play an essential role in ensuring that engines operate effectively throughout their life cycle while minimizing costs, maximizing safety.